with the monster turnout. Please excuse my voice. I have a little bit of a cold, so I'm going to be hacking and coughing as I emote. I don't know if everyone in the back of the room can hear me. So I feel like I should pull up a chair.
Yeah.
Oh, pardon me. So if you want, you can join over here so it's a little more intimate. Either way, up to you, up to you. Okay, make sure, yeah. I feel bad talking with my back to you, but with just the couple of us. All right, so I'm coming from UC Santa Cruz, but as I mentioned a minute ago, I did my PhD here, finished in 2009, and went back to industry, and then went to Harvard, came back here to my hometown area. So when we think of robots, most people think of something like this or like this. But of course, the people here think more like something like this. But maybe going forward, we can think of putting robots someplace like here or even here. But what are the? I'm going to go a little bit quickly because I have a lot. So, what are the? Oh, pardon me. What are the things stopping us from having things like that beyond my cold? I'm sorry, I'm getting over something here. Pardon me. So there was a company, Nightscope. I guess they still exist. Some of you may have heard about them. They have this mall walking robot that does surveillance and things like that. Hotels. I don't know if this is only a rental. They won't sell it to you. Okay. Well, let's hope he didn't have this next headline, because as soon as you have something like this, you start getting headlines like that. You guys may have heard about that. So everything was okay. The kid was all right, and they got the tour of the factory. Everyone doing thumbs up. But if you ask me, mom doesn't look very happy there, despite the nice factory tour. So have you guys heard of Robert Williams? Yeah, you guys have? I guess the two people who want to show up are into this enough to know why he's famous for the first human killed by a robot. So it doesn't take a whole lot of headlines like that before, in addition to a real danger, there's also a perceived problem. People don't want to hear about that sort of thing. When I was here, Bob Full told a story about in Japan, there was a robot company. They had a robot that was supposed to give a hug to the prime minister's daughter. And she said, "I'm not touching that thing." So one of his assistants went and got the hug, and it broke down while it was hugging him, and they had to call out the technicians to unlock the person. I wish I could find the actual story, but anyway, on to bigger and better things. I'll go through this part a little bit quickly. It's administrative and engineering solutions. So there's a fundamental impedance mismatch between the human body and soft biological tissues. And so there are different ways of dealing with that. Looking at a compliant robot, two different definitions. Let me see if I get definitions of compliant, administrative, and engineering. And of course, we have to look at both of those. So there are administrative solutions. I guess the color isn't showing up real well here. It doesn't really matter too much. Going through quickly, it's basically saying, pardon me. Robots are machinery. Let's just treat them like machinery. No, let's treat them like robots that can't hit anything. No, that's not good enough. Let's make them small and weak. I like this one that they used, the pain onset level. It seems to me like a very German way of measuring things is at what point is this going to hurt you, and let's just stay right below that. So our neighbors down the street did the head injury criteria back in 2004, where they said basically how is something going to hurt you and how much likelihood is it going to hurt you. The Puma 560 is right about there. What person is that? I don't know who he is. It's a person just for scale. Postdoc for scale, we can call it. It was a nice picture of the Puma 560 I could get with a human in it to judge the size because of. I'm sorry? You worked on the 560? Oh, wow. So universal robots, they use the same idea, reduce the size and strength and speed of the robot. So you take the best things about robots and say, well, let's just not do that when humans are around. So not necessarily the best solution. And personal robots, make them small and slow so that they just can't hurt people. So nice idea for that type of thing, but isn't necessarily the best all around. Under actuated gripper, it doesn't, is this going to play? I may have to stand back here because it doesn't look like this is going to. So under actuated gripper, that's one way to take first steps towards softness. Still calling it compliant because it's not really soft yet. This wasn't mine. This is to illustrate. It's independent degrees of freedom. Each finger is one independent degree of freedom. I had nothing to do with the design of this robot. So this one I had a little bit more to do with, but I still can't claim ownership for that either. Survival Research Labs built a massively underactuated spine robot with parallel aluminum spines separated by elastomers. You see here the way something like that moves. It's really an elegant machine, especially for something that's essentially built in a garage. Mark is an artist who just builds. Are you familiar with Survival Research Labs? It's called Survival Research Labs, SRL. It's an art group in San Francisco that moved up to Petaluma. Ken was involved years ago. Pauline? He's friends with Ken and Eric Paulos. Okay. So there's a fair amount of overlap there. So another area, series elastic. Good old Rod Brooks here with his Baxter and the Mecha robot using series elastic. Basically taking the idea of taking the things we know about actuation, the things we want, flipping that on their head, saying let's do the opposite. Saying rather than minimizing this, we want to separate the arm from the driver with a spring to give us not the minimum of this, but something in the right range to give us the performance that we want. It's all about there finding the sweet spot, if you will. So using these compliance and built-in compliance and springs and things like that, how can we build something like this out of soft materials? Can we resolve these by building inherently soft materials? So what do we mean by soft? 10 to the 4th, 10 to the 9th pascals, rather than up here where we have aluminum and steel, traditional engineering materials. Can we build things out of elastomers like PDMS? So taking something like this that we just saw bopped a little kid and everyone was unhappy, can we build something more like this? And to do that, of course, all of the parts in this have to be replaced in order to get to something like this. So where do we start? We can start thinking about actuation, fuel, conversion, and control. But once we have the actual physical subsystems down, these aren't out-of-the-box components, so we have to figure out how to put them all together. We don't have a breadboard with resistors and capacitors the way we do with traditional components. And then how do we build such a thing? We don't really have those. So starting with actuation, pardon me. Thinking about essentially a balloon. Concept here, you take a balloon, you blow it up, it blows up as a circle. If you took a piece of tape, essentially inextensible, you blow it up, now it bends at an angle. You do this all the time. Okay, sure, fair enough. So you can do those arbitrarily complex balloons with extensible materials. So here's an extensible one lifting a heavy thing, a light thing. This one's nice because it's fault tolerant over here, still picks it up. Spiky things. This is a group called Soft Robotics Inc., and it's George Whiteside's spin out. Somerville, Massachusetts. It's spun out of Harvard. So, shape memory alloy. Dielectric elastomer just down the street here. Gripper, let's see if this works. It doesn't want to. Anyway, you guys are familiar with jamming grippers. So, and then McKibben actuator. In a way, you can abstract it and think of this as, is it going? No, it's not going. Let's see it. You can think of a McKibben actuator as kind of an abstracted version of the balloon that we talked about where the inextensible layer just reconfigures itself as you inflate it and deflate it. These are really nice for making wearables because they can act as artificial muscles.
That's your stuff.
That was mine. Yeah. So if you guys already use these here, this is all familiar, whether the ways you can get actuation through an inextensible layer or different elastomer materials. And you can get, pardon me, different forms of locomotion, different forms of actuation based on that. You've probably, if you're doing soft robots, you've seen these. I'll just move forward then. So if you're going to have something, of course, looking at these, please ignore the tube to the $1,000 of compressors and controllers. But what do you want to do then? Then you can take it, put everything on board, and essentially you have an untethered device, but it's kind of more of a soft rigid hybrid system. It's a tether to a compressor. That tether is just that long. So we saw tethered to electrical or vacuum or pneumatics and control, wearables with some of the same things, or local onboard. So what can we do? Can we design a fabrication strategy for entirely soft robots? Pardon me. And can we build a system that'll actually show that? So looking more now at fuel and energy conversion, we have a whole good number of strategies with basically these type used in traditional soft robots and a lot of other, fortunately more energy dense methods, but they have their issues. We can ignore these right away because they all require rigid components. So here's some work with a methane based. That's real nice, but it still requires a tether to an external tank and electrodes to fire it, to ignite it. You can do the same thing with butane, but again, you get the same thing, essentially a soft rigid hybrid, which was one of the selling points here. I think, let's see if there it goes. Where you have essentially a lighter and an ignition. So the unfortunate part there is that then you still need all the rigid components for the stoichiometry and the ignition. So how about hydrogen peroxide? Hydrogen peroxide is really nice. H2O2 becomes H2O and O2. We see here some early work done. These are actuated with hydrogen peroxide, but they still used a lot of rigid components for distribution and reaction. Here's some Goldfarb work at Vanderbilt back in the day, but there's no attempt there to be soft. It's just using that. The problem with this is that they're not using the best part of hydrogen peroxide, is that all it needs is exposure to a catalyst to decompose. So you don't really need anything else. You just have to figure out how to do that. And hopefully that's not me with an eyedropper standing over the robot. So take a small amount of the platinum black catalyst, which is ultra high surface area form factor, and we can make a hydrogel out of that and put it somewhere inside of our robot. The bad part about that is at 90%, it reacts vigorously, where the elevated temperatures burn off the organic material. So at 50%, it does not do that, which we can see aqueous hydrogen peroxide levels off, of course, at 100 degrees C, but slightly over 60%, the temperature spikes because you have enough energy to burn off all of your water. You want to be somewhere here. So we chose 50% because it's far enough that we don't hit the elbow. But it's a good amount. So we took 90% torpedo propellant and watered it down. So that's the one we chose. Pardon me. So how would you control something like this? So that's the beauty of choosing the hydrogen peroxide, is you don't need all of this. We said, let's turn to the people, the good folks in the microfluidics field. So microfluidics, I don't think I have to tell you too about this, but this is the Quake Valve, and this is George Whiteside. So these are the guys to trust on this, and they say that it's if you deal with very small amounts of liquid and you have very small features to move the liquid around. Did you have a question?
No,
okay.
I'm just less familiar with the microfluidics.
Oh, okay. Yeah, so That was co-invented by Stephen Quake here at Stanford and George Whitesides at Harvard at about the same time in 2000, so they get to both take credit for it. And the nice thing about the microfluidics is that it often uses silicone rubbers, such as PDMS, and it's the same material that some contact lenses, especially the older contact lenses, were made of.
What is the microfluidics? What is it actually?
What it's used for?
No, what is it chemically?
Microfluidics is just the chamber.
Oh, that's just.
Yeah, it's microfluidics is this plastic that allows you to move tiny amounts of liquid around. It's used largely in DNA sequencing. So pretty much all of the DNA that people do, the DNA stuff, they use microfluidics. It's also used in inkjet printers. Whatever you want. In DNA, it's different reagents in order to get things to move around, and you can control them externally using.
And in robotics, what do you use?
In this case, it's hydrogen peroxide. To the best of my knowledge, we're the first people to use it to control any robot, especially a soft robot. So the concept is you take a wafer, maybe this will answer a couple of the questions. You take a wafer, put all your traces in there for a negative, you cast your elastomer on top, cut it out, you O2 plasma bond them to have an enclosed chamber with selective features in different places, and you have an encapsulated circuit.
So what is that on the right side?
This is the controller that we use, and I'll cover that more in just a minute.
And what is it made of?
This is all PDMS. Silgard 184. This is definitely not the limiting factor. The actuators tend to be far less precise.
That's what I mean.
Yeah. Well, this is only the controller. This isn't how you make the actuators.
It doesn't move. I see.
This moves on the microscopic scale, just enough to allow the flow of the liquid fuels.
But then
So you take your PDMS device. The concept here, kind of what we just talked about. This is the Quake model, the Quake Valve, one of the first devices. You have a control line and a flow line. So you have gas flowing through here, and you have a liquid flowing through here. And you want to control that. So you have flow and no pressure. When you turn the pressure on, you occlude the flow. Simple concept, just like the balloon thing. 2 seconds to explain, a lifetime to get all the details. It works on the order of tens to hundreds of milliseconds, which isn't great for a computer, but for a robotic system, that's more than plenty for most applications. So over the years, people have developed a lot of different operators out of the microfluidics, and so I was able to take this and look at it and say, okay, the things that I need to make the simplest device I can as a proof of concept, I need a diode and oscillator. Okay, let me go ahead and build something that's largely, at least conceptually, borrowed out of the literature. So there was an operator here. I think it's the next slide. We can kind of see that oscillates. Here it was like we were talking about for DNA to oscillate reagents, to have different reagents going into your DNA sequence, or in this case going into a paper towel, because it's really just a proof of concept at that end. Saying, well, I want to have 2 inputs, 2 outputs. Let me modify that design in order to get something from that gives me what I want 2 outputs. I don't really care how many inputs I have. It's because something existed that has 2 inputs.
the outputs are basically different in the direction which way you move.
So it's more simple than that. I wanted to have alternating actuation.
Okay.
This robot doesn't lift itself up and walk around.
Okay.
It actuates its limbs. So this uses a switch valve in which flow is allowed or occluded, and a similar technology, a check valve, where the same direction flow is either allowed or occluded with back pressure. So having the basic components, how do we put them all together? I laid out a nice sketch of how this type of thing would work conceptually, which is always a lot easier on paper than to actually build it. So the concept is you fill up your fuel tanks here, and they, through elastic strain energy of an elastomer, will force their way down through the system. One side will be slightly higher pressure than the other. In this case, let's say blue's higher, and it forces its way past red, pinching that off. So it goes downstream, it hits the platinum reaction chamber. It reacts, the H2O2 breaks down into H2O and O2. So a small amount of liquid becomes a whole lot of gas. That large amount of gas flows downstream, actuates all of the actuators, and continuously vents to the atmosphere. So that's the concept. That keeps happening until blue is slightly lower pressure than red, at which time red forces its way through, pinching off blue. Blue continues to vent. Red decomposes, actuates downstream, and that keeps on happening until it's below the level of the blue, and then it switches. So starting with this, we have initial pressure that degrades over time, but oscillates downstream in an alternating fashion, which causes the reaction, and then a smaller actuation, which degrades as the pressure goes down. And
it's just showing like 3 or 4 motions on each side, and then it's dead.
it varies how much. We inflated with 1 milligram just for calibration, and it goes for about 4 to 8 minutes. So you can get about 10 cycles, or 10 actuations, so 5 cycles. And that looks like an electric diagram. The number, it's not a numerical equivalent, but conceptually it's equivalent. Concept-wise, on actuators, we can vary the 2 layer thicknesses. It sounds like you guys are already very familiar with that. Based on your different Young's moduli, you get different strains. And tune those based on the different layer thicknesses to get different inflation angles. So take the whole thing, and you don't want to get to an all-around high like in electrical. You don't want to always high, always low. Otherwise, you won't switch or you won't actuate at all. So the whole thing is based on this downstream check valve, making sure that you have enough pressure but not too much pressure, and giving you basically continuous through, but fast enough operation that it'll still switch. So that's all fine and good, and I tried all kinds of fun, interesting things to build this thing. I started laying out different ideas. Here's an elastomeric reaction chamber with some sputtered platinum on the inside, and sure enough, it reacts with the peroxide. So how would I store that? I don't want to have an eyedropper, so fill up a reaction chamber, which decomposes and fills up a plenum, which then can be actuated, causing an actuator to bend. And that's all fine and good. That's all really nice, but this wasn't converging on a solution. How do I build this thing? I looked at layering methods. I looked at lost wax casting, that sort of thing. That's a whole career in itself. Fortunately, that was about the time that I ran into the Lewis lab. They were building these novel 3D printing technologies looking for an application. I had an application. I was looking for someone who could build something really neat.
Which lab?
Jennifer Lewis lab.
Oh, Jennifer. Okay.
Yeah, she was at Urbana-Champaign, and then she moved to Harvard. Yeah. So I met Jennifer and one of her students, Ryan, who was looking for a killer app for his work, and we developed the Octobot using his technology for what he's calling embedded or EMB 3D printing using this. So basically, you want something that has to be shear thinning and have an initial yield stress. You can print the coolest thing in the world in water, and if it just drifts away as you print it, it doesn't do anybody any good. So you have Newtonian and shear thickening. We want something that's shear thinning, but it has to have an initial yield stress so it doesn't float away. So we want an initial yield. And this type of materials we call Herschel-Buckley model, the materials. And that way we can print them using a needle inside of an existing matrix to create an existing trace, a new trace.
Do you want to shear thinning so that the tool itself can move?
Yeah, if you shear through a material, you don't want to disrupt all the material around it. You want it to break down so that you can deposit, and then after you leave, you want it to harden up again so that it'll hold it in place. That drastically reduces your fidelity because you're dragging everything around. You may be able to do one line, but if you want to do true 3D printing where you have multiple traces around one another, that really causes...
Well, because like the purple line at the top.
Yeah. If you have something here, another trace, let's say you have a trace going into the screen here, you can probably get away with more similar to this than that, but the less shear thinning it is, the more you disrupt other features. So you then have less fidelity, and you can't get as close to other features.
Okay.
So less density, less fidelity. All right. So the idea of using this is you can take your device, you have overall features, you can design the macro features. I made these on a mill, and then you put your controller in, fill it with an uncured elastomer, and you can now, without having to 3D print all of your geometry, you can print only the internal features. So you have the benefit of casting and the benefit of 3D printing. So a number of different features, a number of different sized features. What you were talking about, you couldn't really do anything like this, or this, which is made by repeating near one another. You'd end up getting more of a glob if you did that.
What material are you depositing to create these traces?
So you need a matrix material that exhibits those, and you need your print material that's similar but just a little bit stiffer. And what we're using is, they're calling it a pluronic. I think I have a slide later on. I may or may not. How am I doing on time? I better hurry up. It's a copolymer. It's a reverse phase change. It starts as a gel, and then as you reduce it down to very close to zero, freezing, it's aqueous. So it's basically balls, and as you get them close to freezing, they break apart and release the water. So it goes from a gel at room temperature to a liquid near freezing. I'm sorry? That was the idea. That was the idea originally. But fortunately for us, here's a quick video. I'll get to that in just a second. So printing the devices, printing up to here we have, this is the catalytic chamber, printing up to it. The pink is dye added for visualization. Printing the actuators.
Are you trying to build a lab like this in Santa Cruz?
No, I'm not trying to compete with Harvard. No. I want to use a lot of the things I learned from there. And
so what do you plan to do in Santa Cruz?
Well, I still want to work on soft robots. I have a couple slides towards the end that are some of the next projects I've done, and I want to move into this.
Yeah.
Okay. No, I'm happy to hear it. So the thing we didn't expect that turns out to happen is these elastomers, they're very slightly water permeable, especially to water vapor. So when we put this whole thing into an oven to bake out, to cross-link the polymer, the ink, the sacrificial ink, started to auto-evacuate through the wall of the polymer and leave a hollow chamber. So we took it out to try and flush it out of there. We didn't have to. So that was really fortunate because we can do now arbitrarily small features, and we can do dead-end features, which you wouldn't be able to do if you had to flush.
Have you tried that?
I'm sorry?
Have you tried the dead end features?
Yeah, these are all dead ends.
Oh, really?
These actuators are all dead ends.
Have you ever done one that doesn't have any outlet?
Yeah, these don't have outlet.
Completely sealed?
These are completely sealed until I punch them. I take a biopsy punch and punch access holes, but when I pull it out of the oven, it's completely sealed. Yeah. Yeah, so that was a happy coincidence. And that yields, pardon me, the Octobot. Yeah.
Are you building one like this?
Not without any hard.
Well, I think that's a really nice goal, but I don't think it's the only goal. So I'm not doing that anymore either.
I don't know enough about octopus, but do they have a beak?
They do have a beak, but you can't really say that the beak is the brain or the compressor or anything like that. And that's one of the beauty of once we get more functional, fully soft robots, is then we can add hard regions, rigid regions, for design considerations rather than our lack of engineering novelty. So that would be great if we could do things like fingernails or bones, but rather than saying, oh, well, I need a compressor here. So actuating in one direction and the other direction, when the blue is active, it actuates 4 of the legs. When the red is active, is flowing, it actuates the other 4 legs. So we fill it up, remove the tethers. We see it flowing through. When this is blue, blue goes. When it's red, red goes. And it's continuously venting.
Is it so slow that you have to do the 10 times playback?
Well, it's on the order of 10 to 30 seconds, depending on when you get it. And here's from the front. You can see the leg actuations. So is it slow? Yes, it's slow. There were other concepts evaluated, but this was the one that was showing the most success, so we moved forward with that. So in short, we made a completely soft, autonomous, untethered robot, but it's clearly a minimal demonstration. No one says, hey, where do I get a robot that sits there and moves legs up and down? There are other things we'd like a robot to do. So there are a lot of things we can do that we would like to do more sophisticated. When we look at this, we did all of these things, but what's missing from something like this? Probably some sort of sensors. Well, you know, technically you could think of these things, if you compress them, that blocks the upstream, so then it has some sort of body intelligence, some sort of morphological computation. But that's very baby steps towards morphological computation. Yeah. You know, you could say that if the leg hits an obstacle, then that would pinch off a valve somewhere internal and cause it to actuate the other actuators. But again, that's future work. This was enough work. So my family is still upset about the late nights. I didn't come home over this. So there are some sensors, soft actuators with sensors. It sounds like you guys are working on this. You probably know about a lot of these. So we have this one, like you said, the Daniela Roos area. This is Rob Shepard's waveguide version. But this is really simply integrating traditional sensors, and this is using some less than optimum sensors that need to be manually created every time and have a lot of flexion.
What kind of sensors you are using?
Me? These aren't me. This is a waveguide. Waveguide. It's like a fiber optic. Okay. But it's through an elastomer, not through yeah. So another type of sensor, these carbon grease sensors. Here you see one being 3D printed. And they're nice. They can be stretched. They have multiple direction sensors. Sounds like you're familiar with those.
I've seen this.
Okay. Yeah, it is. The carbon grease, however, it's carbon and it's grease. So as you stretch it and return it, it never comes back in exactly the same configuration. So you have a lot of So the concept here, it sounds like you guys know about this, is if you have a trace of a certain diameter, of a certain shape, and you have a liquid or gel inside of there, you have a length and a cross-section area. If you stretch it, you have now a different length and a different cross-section area. So as the length increases, area decreases, your resistance goes up. So you will need to find a material for the inside that has a nice resistance. You don't want something with pico ohms. You don't want something with giga ohms. You want something that's going to behave nicely in this, that you can measure easily, especially for a mobile system. You don't want to say, here, carry this backpack to process your signal and find your resistance. Another one, which maybe you were talking about briefly, is eGain. It's a eutectic of gallium and indium. Eutectic of gallium indium. And that is basically like a mercury, but not horribly toxic. And that has a lot of nice parts. It happens to be very relatively highly conductive, but it also has a propensity to oxidize. So as you push it through your channel, you can't 3D print it because it doesn't exhibit these behaviors we talked about. And as you push it through the channel, it has a leading edge of oxide layer. Also, as we talked about, this is very slightly permeable to water vapor, which means you'll natively get oxide layers. So the people who do this, they have a process step where they scrunch on it with their fingers to get the oxide layer out every time they start an experiment. So here's a nice video of them infilling one. This is a 3-dimensional sensor. We'll see it operate at the end. This is someone extracting here and compressing here. And you go around and almost there. Now this next part is pretty cool. I wish I could take credit for this. 3-dimensional strain sensor. That's really cool. I think the material itself has a lot of issues, but I think that demonstration really shows exactly what people want to see there. And here's the waveguide based version. Sensing touch. Squishing tomatoes to see which one is ripe. Yep, that one's right. So different types of sensing we would want to do following the human sensing: proprioception, fine touch, harder touch or pressure, and some sort of other form, pain or temperature. We did temperature because I don't know exactly how you define pain in this.
All those things that we have so naturally.
Yeah, and we don't even think about. And it is a big, messy, noisy signal, but somehow our brain knows how to take that and say, oh, someone's poking my finger. So we developed this, which has bladders for actuation and different sensors for different modes of sensing, including, so it's attached here, and then there are touch sensor, bend sensor, curvature sensor, and inflation sensor in between.
Curvature sensor.
I think the next,
Reflection.
yeah, it's like we showed before about the stretching. This is stretching, but just around an angle. So we do it this way. See, it's up above along the top here.
Yep.
Yeah. And so that senses curvature and inflation, which I think shows best in the next slide, using different types of matrices and different types of inks. So the curvature is here, touch is here, and inflation is here. It weaves in between the muscles. That, I don't know if it's as important for day-to-day first step control, but it's really interesting that we can build something like that in between the, and I think that's the one sensor that really is hard to do with any other technology. There, so.
Who built this?
This was Truby, the guy who did the 3D printing with me, and myself, and a bunch of people at Harvard.
I saw this hand. Yes.
Yeah?
Yes. How? Where is it? Do you have it?
No, it's at Harvard.
It's at Harvard.
Yeah, it doesn't belong to me, so it stayed. When I came, it stayed.
I love to copy this.
Yeah?
Yeah, sure. You have a design for this?
Yeah, I'm the one who designed it, so
Yeah.
yeah.
You must have computer-aided design.
The files, yeah, of course, I certainly do. Yeah, so with these types of projects, what we've done is I've done the electromechanical design, and Ryan did everything 3D printed related, which is why I can't give as detailed of an explanation about Herschel-Buckley materials and thixotropic and what range he did his whole PhD in it. I'm more of an avid amateur. Well, thanks for coming out.
Yeah, so I'm gonna have lots of questions, so I'll just let you.
Okay, I think at this point, especially because it's such a huge overflow, keeps me humble, right? So looking at this device, we see the bladders and the sensors and the type of things we can do with it. And it's really interesting and really exciting, but it's really so far just open loop and demonstrating the possibilities of sensing. So now this opens the door to more questions than it actually answers. And I believe, aside from the most important part, is thanking the people I've worked with and the people who were generous enough to make this all happen, and the individuals. If she could have stayed a couple more minutes and said, who did this, I could have showed her who did this. Yeah, I can go to questions now.
Yeah, sure. I mean, I more just have comments and interest in that last part, the sensing. So,
Oh, okay, great.
like, in those channels, how is the sensing actually happening? So you have a fluid there.
Yeah, and it's a
and
conductive
it's-
fluid.
And it's conductive and it's throughout the entire channel.
The
so-
fluid is wherever you put it. And
In this finger, where is it?
let me go to the CAD is a little easier to see, of course.
So you have the.
Yeah, here. So
So
it,
it doesn't look like it's going throughout the entire finger. It's like-
this you mean?
Yeah.
What happened was we put it through the entire finger, and then the resistance, we talked about, there's a matter of getting the sweet spot in the resistance. And so we had it connect up here, because it's a three-dimensional. Let me see if I can find it. So it connects at the end here, but it turns out that our resistance was too high. So we said we want to stop it here, but then we built them with just this much. And we said now our material properties are different because we just added a bunch of elastomer here where there used to be essentially a void. So we still print it, but we connected it here so that this is the only functional component. The rest is just for homogeneity and actuator.
Are you relying on the fact that it's a compressible material in there to get more sort of, there's no air gaps or bubbles inside of these channels?
There's no air gaps or bubbles. If there are, you have problems.
Yeah.
You print them as is. The biggest problem is what we talked about that turned out to be the big benefit for Octobot, that it auto-evacuates because it's semi-permeable to water, is that this is also semi-permeable to water, and it goes the other way. So you have this ionic fluid, which changes properties based on humidity. So at first, that seemed like it was going to be a big problem. But we said, what can we do here? What are the properties? Let us understand rather than just saying, oh, it's sensitive. I'd better go home and think of something else. Let's explore it. It turns out that it saturates at about 7 days. So if you build it and let it sit for a week, it just has to sit for 7 days. If you have an emergency, you can bake it and get it to the other end of the saturation limit.
But if you submerged it in water, let's say, so then it wouldn't matter because it's already.
If you submerged it, at equilibrium. If you submerged it in water for a few hours, you'd be fine. But if you want to have something that's amphibious, where it goes into water, comes out of water, and operates for a week out of water and a week in water, that would be more. That's a lot more characterization. Who knows? Maybe, maybe not. So I am looking at doing some underwater stuff.
So that's really where my interests are. Yeah. So if you have time after this, we could.
Absolutely.
Go back to my office.
Yeah, I'd love to. Yeah. I have a collaborator at University of Rhode Island who does deep sea exploration.
Oh, is that Brennan?
Yeah.
Okay, I talked to him. So yeah, we should.
Okay, yeah, for sure, yeah. So we unsuccessfully applied for a grant to do some of this. Yeah, I was expecting to get every grant I applied for. So, so, did you have any other? That's it? Oh, okay, great.